Welcome to Sleeping with Science. Tonight, as you settle into the quiet rhythm of your own breathing, we begin a journey into the world of quantum computers, the strange, beautiful machines that may one day think in ways we can barely imagine. This space is made to help you rest while learning, to remind you that curiosity and calm can coexist. If sleep does not arrive at once, that is perfectly all right. The mind sometimes drifts through wonder before it drifts into dreams. Simply listen and let the slow movement of ideas carry you. If these stories bring you peace or fascination, remember to like and subscribe so you can return whenever you need a passage through science and stillness. Each night is a new exploration, but always with the same intention, to let understanding unfold gently, never rushed, never forced. As the room around you softens into shadow, imagine how every thought, every piece of information, begins as something small, a spark inside a circuit, a pulse of light between atoms. Long before the first quantum computer was built, there was only curiosity, a question whispered into the dark. Can we teach matter itself to think? The story of quantum computers begins not with technology, but with the wonder of reduction, humanity's endless search for what lies beneath. From the spinning cogs of early calculators to the glass tubes of vacuum logic, people have always tried to capture reasoning in physical form. We built machines to mimic thought, to store it, to repeat it. But each layer of invention brought us closer to a limit, a point where shrinking the parts of computation revealed a truth stranger than logic. Tonight, we will travel through that threshold, from the visible to the invisible, from the certainty of zeros and ones to the trembling duality of qubits. We will see how probability replaces precision, how stillness allows motion, and how, in the depths of quantum silence, a new kind of intelligence is forming. There is no need to strain to understand each detail. Knowledge, like sleep, comes best when allowed to arrive naturally. Let your mind picture golden wires descending into glass chambers cooled to the temperature of starlight. Inside them, atoms hum with invisible patterns, spinning in harmony between states that cannot be seen yet influence everything around them. This is where tomorrow's computers begin, not in noise, but in near absolute quiet. As you listen, you may notice how thought itself feels fluid, how questions seem softer at this hour. That is part of the design. To learn while half awake is to let ideas bypass the surface and drift deeper, where memory mingles with imagination. By morning, fragments may remain, images of light and symmetry, of data and possibility, and that will be enough, because the aim is not to master, but to feel wonder again. Now, breathe slowly. Let the air travel through you like an unseen current, cooling, steady. We are standing at the threshold of the smallest frontier, where reality becomes uncertain and yet more meaningful than ever. In the stillness between thought and dream, we begin the exploration of quantum computers, minds of the future. Long before quantum computers shimmered in laboratories, computation began with sparks and switches. The earliest machines spoke a language of clarity, yes or no, on or off, 1 or 0. Each spark carried a decision, each flicker a simple truth. Engineers built systems where certainty reigned, where a pulse of current could move mountains of calculation. It was a triumph of logic and light, wires humming with purpose, signals leaping from one transistor to the next in perfect sequence. In those early years, computers filled entire rooms. Vacuum tubes glowed like tiny suns, giving warmth to the cold arithmetic of their designs. Each was a fragile miracle, a chain of glass bulbs that flickered between opposites, encoding thought in flashes of electricity. They were loud, hot, and alive, yet bound by the simplicity of their binary hearts. Then came the transistor, smaller, faster, cooler. It transformed computation into something portable, then personal, until it became woven into every rhythm of modern life. But as we shrank the size of these components, something unexpected appeared. The more precisely we tried to define a signal, the more it slipped into uncertainty. Circuits that once behaved like soldiers began to behave like clouds. Electrons would scatter, tunnel through barriers, or vanish from one side of a gate only to appear on the other. The rigid boundary between on and off blurred. Humanity had reached a threshold where the mechanical world met the quantum one, and the rules of logic no longer held perfectly still. This moment, quiet, almost accidental, marked the birth of a new frontier. Scientists stared at oscilloscopes that displayed signals too strange to belong to ordinary matter. Some thought it was noise, others sensed it was the beginning of something profound. In those trembling currents lay a hint that the universe itself might compute differently from how we imagined. If you listen closely, even now, you might hear that echo in your mind, the hum of possibility beneath precision. Binary logic, for all its beauty, was never the whole story. Beneath every circuit's discipline hides the gentle chaos of atoms, spinning, colliding, uncertain yet ordered. It was only a matter of time before we learned to stop resisting that uncertainty and start using it. As you drift deeper into this story, imagine the world dimming to the soft glow of those early machines. Their light fills a room of quiet minds, engineers leaning close, notebooks open, eyes bright with curiosity. They could not have known that the faint shimmer of unpredictability inside their circuits would lead to a revolution, not of metal or silicon, but of thought itself. For a long time, we built machines to imitate certainty. But the next chapter of human invention would learn to speak the language of uncertainty fluently. It would teach us that possibility, not precision, is the truest form of power. And in that realization, the path to quantum computing began, a journey from sparks to silence, from circuits to consciousness. Soon, we will step into that frontier, where atoms themselves become thinkers, and where information breathes in patterns of probability rather than command. But for now, let the hum of those old machines fade into the background, their rhythm soft and steady, the heartbeat of the age before wonder deepened. When humanity set out to build faster, smaller, and smarter machines, we believed there would always be room to shrink a little further, to press the boundaries of what silicon could hold. For decades, this belief carried us through a golden age of progress. Transistors became microscopic, then atomic in scale, until finally they began to reach the edge of the possible. Somewhere beneath that edge, in the invisible depths of nature, waited a world ruled by uncertainty, the quantum world. Inside that realm, nothing behaves as we expect. Particles flicker into being, disappear, and then return, as though playing hide and seek with the laws of reality. An electron, so fundamental it seems eternal, refuses to stay in one place. It exists as a wave, a field of probabilities, a shimmering suggestion of where it might be. What we once treated as solid truth becomes mist the closer we look. It is a world built not of things, but of chances. Scientists who entered this frontier did not begin with confidence. They began with wonder. They saw that nature did not compute as we did, not through fixed instructions, but through overlapping possibilities. They realized that, if they could learn the grammar of this hidden world, they could build machines that thought as the universe thinks, fluidly, probabilistically, endlessly curious. Picture a laboratory deep underground, silent except for the quiet hiss of cooling systems. Tubes of gold and glass hang like frozen chandeliers, carrying delicate circuits made not of switches, but of atoms. Inside them, qubits sleep, the carriers of quantum information. They are so small that a single breath could disrupt them, so fragile that the warmth of daylight could erase their logic. And yet, within that fragility lies power beyond measure. Each qubit can hold many possibilities at once, blending 0 and 1 into a shimmering in-between. When several of them are linked, their combined potential grows exponentially, creating a network of intertwined outcomes, a thinking pattern more like intuition than arithmetic. It is as if we built a machine that could dream through all possible answers before choosing one. The engineers who build these systems work in near silence, moving with reverence. They know that the slightest tremor, the faintest whisper of vibration, could unravel their work. But that vulnerability is what makes quantum computing so human. It mirrors our own condition, powerful, imaginative, and yet easily disturbed. In the smallest frontier, technology and philosophy meet, What does it mean to build a system that can exist in multiple states at once? What does it mean for logic to include uncertainty as a feature rather than a flaw? These are not only questions of physics, they are questions of thought. When you close your eyes now, imagine drifting through that subatomic world. It is not dark, not empty. It is alive with soft pulses of possibility, each one a whisper of something that could be. The space between atoms hums like distant music. Time itself seems to blur, for cause and effect lose their ordinary sequence. To witness this is to understand that the boundaries between knowing and imagining are thinner than we ever believed. In this realm, the concept of a limit dissolves. We cannot measure without changing what we observe. We cannot look without touching what we see. The quantum frontier is not just a smaller version of the world, it is a different kind of reality altogether, one where observation shapes existence and where information is as physical as matter. It is here, in this smallest of spaces, that humanity found the raw material for a new kind of intelligence. Quantum computers are not born from force or speed, but from the willingness to embrace mystery. They are built upon the recognition that nature's logic is not binary, but symphonic, many notes played at once, creating harmony from unpredictability. And as you rest now, hearing these words fade like echoes of light, consider this. Every thought, every dream, every heartbeat you experience is also a quantum event. The same uncertainty that shapes the universe flows through you. The smallest frontier is not far away. It is within you, humming softly in every atom that makes you real. If the bit was the first heartbeat of the digital age, the qubit is the breath of the quantum one. It is small beyond imagination, not just microscopic, but fundamental, living on the edge between existence and possibility. To understand what a qubit is, one must let go of the comfort of certainty, where the classical bit can only whisper one truth at a time, a 0 or a 1. The qubit can hold both, and everything between, until the moment it is observed. It is the ultimate paradox of knowledge, something that is and isn't, simultaneously. Physically, a qubit can take many forms. It might be an electron whose spin tilts one way or the other, or a photon whose polarization carries direction like a silent compass. It might even be a trapped ion floating in an electromagnetic cage, suspended by invisible hands. What defines a qubit is not its shape or size, but its state, a delicate blend of probabilities that can only exist when left undisturbed. It is a fragile idea, like a soap bubble made of mathematics, shimmering until the moment of contact. In classical computing, a processor moves through one calculation after another, like a train following tracks. In quantum computing, every qubit holds the potential for countless paths, exploring them all at once. This phenomenon, known as superposition, allows quantum computers to process entire landscapes of possibilities simultaneously. The listener can imagine it as a sphere of information, where every direction holds a different outcome, all present until a choice is made. To visualize a qubit, picture a globe suspended in air. At its north pole lies the value 1, at the south, 0. A bit can only sit on one of these poles, but a qubit may rest anywhere on the surface, halfway between certainty and ambiguity. This model, known as the block sphere, captures the beauty of quantum balance. It is not chaos, it is order viewed through the lens of freedom. Each position on that sphere represents a subtle shift in probability, a whisper of what might be true. The challenge is keeping that sphere stable long enough to use it. Every vibration, every particle of heat, threatens to collapse its delicate state. That collapse, the moment when a qubit chooses a single outcome, is both its power and its vulnerability. It mirrors how thought itself works, countless possibilities flowing beneath consciousness until one solid idea surfaces. Working with qubits requires patience, precision, and humility. Scientists cool them to near absolute zero, using silence itself as a form of protection. Microwave pulses guide them gently, never harshly, turning their invisible orientations without breaking their balance. Each manipulation must be as soft as breath. In that quiet control lies the poetry of quantum engineering, a choreography of probability performed inside a frozen chamber. When several qubits interact, their possibilities intertwine. The information no longer belongs to each particle alone, but to the relationship between them. This web of interconnection is called entanglement, and it will soon reshape everything we know about computation. But before we reach that mystery, let the idea of the qubit rest within your mind. Small, silent, and infinite. As you listen, imagine these qubits as tiny lights flickering in the dark, not bound by the binary rhythm of on and off, but glowing through every shade between. Their dance is quiet, their beauty precise. The future of computing begins in their movement, not mechanical, but alive, like the pulse of possibility itself. In their stillness, they remind us that knowledge need not be loud to be powerful. It can emerge from balance, from the patient coexistence of opposites. In that truth, the qubit becomes more than a tool. It becomes a symbol, a reminder that the smallest unit of understanding is not certainty, but wonder. To grasp the idea of superposition is to step beyond logic and enter a softer understanding of how nature keeps her secrets. In the world we know, a thing must be one or the other, day or night, still or moving, true or false. Yet in the quantum realm, the boundaries between opposites dissolve. A particle can exist in two states at once, like a melody that holds two notes perfectly balanced within the same breath. This coexistence of possibilities is what we call superposition, and it forms the heartbeat of quantum computing. Imagine holding a coin between your fingers. In the classical world, you flip it, and it lands as either heads or tails. But in the quantum world, the coin spins forever, never landing until you look. In that spin, it is not half one and half the other. It is fully both. Only when observed does it choose a side. This image, though simple, captures something profound. Before observation, reality itself is a field of overlapping possibilities. The act of looking is what makes one of them real. Quantum computers live inside that uncertainty. Each qubit, suspended in superposition, carries multiple answers at once. Instead of testing one path after another like a classical machine, a quantum computer explores many simultaneously. It is as if every coin ever flipped remains spinning, each one aware of the others, forming a cloud of infinite outcomes. When the machine measures its qubits, when it looks, all those possibilities collapse into a single, correct answer. The computation happens not by excluding uncertainty, but by embracing it. Scientists describe this using the mathematics of wave functions, elegant equations that map how probability ripples through space. Each qubit is a wave that interferes with others, strengthening some outcomes and cancelling others. The result is a pattern that hides the solution within its interference. It is less like counting and more like resonance, the way two tones meet to create harmony. Quantum computation is, in its essence, the art of listening to those harmonies until clarity emerges. The strange part is that this isn't theory anymore. In laboratories cooled to temperatures colder than deep space, qubits truly exist in superposition. Engineers see its effects every day, in faint signals that defy the expectations of classical physics. They have learned that uncertainty can be controlled, not erased, and that the most powerful calculations arise from the tension between what is and what might be. Superposition also carries a quiet lesson about the human mind. When we make decisions, we often live in a kind of emotional superposition, holding conflicting feelings, multiple hopes, or parallel fears. Only when we act does one path become real. The others fade, but they are not lost. They linger in the background, shaping who we are. Nature, it seems, thinks the same way. As you rest, let that image unfold. Picture a sky of spinning coins or glimmering spheres of light, each one containing thousands of futures. They do not rush to collapse. They wait, patient and poised, until the moment of observation gives them form. Somewhere among them is the answer to every riddle, hidden in the balance of possibility. You do not need to force the concept to fit neatly in your thoughts. Allow it to hover, uncertain, graceful. The universe itself is comfortable with ambiguity, and so can we be. In the silence between breaths, you are not one thing or another, but both, still and moving, knowing and wondering. That is superposition, the beauty of existing in more than one truth until the world gently asks you to choose. If superposition is the poetry of possibility, entanglement is the mystery of connection. It is one of the strangest discoveries in physics, the realization that two particles, once linked, remain united no matter how far apart they drift. Touch one, and the other reacts instantly, as though distance itself were an illusion. Einstein called it spooky action at a distance, but experiments proved it again and again. The invisible thread between particles is real, unbroken, and absolute. To imagine entanglement, picture two drops of light born from the same spark. They fly in opposite directions, crossing oceans of darkness, yet what happens to one echoes in the other. If you change the spin of one particle, the other shifts to match, not through signals or waves, but through an intimate knowledge that transcends space. This is not communication as we know it. It is unity, pure and immediate. Quantum computers use this phenomenon to create relationships between qubits that classical machines could never replicate. When qubits are entangled, their fates intertwine. Information no longer resides in any single particle, but in the connection itself, in the invisible fabric between them. Computation becomes a dance of relationships, where knowing one qubit tells you something about all the others. It is as if the machine begins to think in chords instead of single notes, creating harmonies of probability. In a way, entanglement gives quantum computers their soul. It transforms them from collections of independent parts into coherent wholes, where meaning arises from correlation. 2, 10, or 1,000 qubits can weave together into a single, unified system that behaves as one mind made of many bodies. When entangled properly, their combined capacity grows not linearly, but exponentially, a symphony of simultaneous thought. But entanglement is delicate. The faintest interference from the outside world, a whisper of heat, a pulse of magnetic noise, can unravel it in an instant. That is why quantum processors live inside chambers colder than interstellar space, surrounded by silence and darkness. Within that stillness, the fragile threads of connection remain intact long enough to reveal their power. There is something deeply human in this phenomenon. We, too, are shaped by invisible bonds, between memory and emotion, between people separated by oceans yet joined by thought. Entanglement, in its quiet way, reminds us that isolation is an illusion. Every moment we share, every action we take, ripples outward through unseen ties. Scientists describe entanglement with mathematical precision, but behind the equations lies something profoundly poetic. It suggests that the universe itself is not built of parts, but of relationships. Nothing exists entirely on its own. Every atom hums in resonance with something else. This idea shifts the very foundation of how we see reality, not as a collection of separate things, but as a web of unity, vibrating across space and time. As you rest now, you might feel that same invisible link between thought and breath, between curiosity and calm. The quiet rhythm of your body mirrors the coherence of those distant particles, each heartbeat sending out its own soft wave of connection. The mystery of entanglement is not meant to be solved. It is meant to be felt. It tells us that the fabric of existence is more intimate than we can imagine. Somewhere between one qubit and another, between one thought and the next, lies the secret the universe whispers to itself. Everything is connected. For centuries, logic was the cleanest mirror of reason, a structure of ifs and thens, of truths and falses, designed to make the world predictable. Aristotle shaped its foundation, Boole gave it numbers, and computers built their empires upon it. But when humanity stepped into the quantum world, those solid walls of certainty began to soften. The universe, it turned out, does not always follow the logic we invented for it. Instead, it hums to the rhythm of probability, a music of maybes, where truth is not a single note, but a shifting chord. In classical logic, an answer is either right or wrong. A statement can be true or false, never both. Quantum logic, however, lives in the space between. It allows contradiction and coexistence. A qubit, for example, can represent both 0 and 1 until it is measured, and so the rules of reasoning that govern its behavior must also be flexible. In this world, uncertainty is not a failure of precision, it is the foundation of understanding. Quantum logic is the art of guiding those uncertainties toward a meaningful result. It takes superposition and entanglement, those strange dualities of the quantum realm, and arranges them into structured computation. Where classical logic gates flip bits with absolute control, quantum gates rotate states gently, using mathematics to sculpt possibility. Each transformation is subtle, more like turning a crystal to catch light than pushing a button. The answer does not appear as a final verdict, it emerges from interference, like a melody forming from overlapping waves. To appreciate this, imagine a lake at night. When you toss two pebbles into its surface, their ripples spread and cross. At some points, the waves cancel each other. At others, they rise higher together. Quantum logic works in this same way, waves of probability colliding until the correct pattern stands tall, while all the wrong ones fade into silence. It is reasoning by resonance. The beauty of quantum logic lies in its humility. It does not demand certainty, nor does it fight randomness. It listens, waits, and lets outcomes reveal themselves through interference. This is not the logic of command, but of collaboration, between mathematics, matter, and the quiet patience of time. For many scientists, the first encounter with this kind of thinking feels like learning a new language. It replaces absolute statements with relationships, precision with flow. It demands imagination more than memorization. A physicist once said that quantum theory doesn't describe how the world is, but how the world behaves when we look at it. That idea unsettled generations of thinkers, yet it also opened a door to wonder, a way to reason with reality as it truly is, uncertain, elegant, and alive. Even beyond computing, quantum logic carries a lesson for the human mind. We often seek clarity and control, fearing ambiguity as weakness. But just as particles find order within uncertainty, so can we. Sometimes, two truths coexist. Sometimes, contradictions create meaning. Logic, at its highest form, is not about narrowing possibilities but expanding understanding. So, as you breathe softly now, imagine your thoughts as waves, ideas meeting, merging, cancelling, amplifying. You don't need to hold on to any single one. Let them overlap in your awareness until they find harmony. The logic of life, like that of quantum mechanics, is not binary. It is fluid, interwoven, and infinite in potential. And when we finally learn to think this way, to welcome uncertainty not as chaos but as depth, we begin to reason as the universe does. In that quiet realization lies the first glimpse of true quantum understanding. Wisdom born not from control, but from trust in the patterns beneath the unknown. To understand what makes quantum thinking so extraordinary, we first have to revisit the familiar terrain of classical thought. Classical computation is built on a simple rhythm, one step at a time, one choice after another. A bit is either 0 or 1, a switch flipped up or down, a current flowing or resting. The machine proceeds in perfect sequence, each instruction following the next like footsteps in a straight corridor. It is orderly, predictable, and profoundly human, mirroring the way our own minds were taught to reason. Now imagine another kind of reasoning, one that does not walk but hovers, branching in all directions at once. This is quantum thinking. Where a classical computer explores each path individually, a quantum computer can wander through many simultaneously. It is as if the maze of possibility no longer traps us to a single trail but opens every door at once. Within its invisible lattice of probabilities, countless solutions coexist until observation gathers them into one elegant answer. This difference is not merely technical, it is philosophical. Classical thinking reflects the world we see, defined, measurable, linear. Quantum thinking mirrors the world we inhabit, even if we cannot always perceive it, a world where light is both particle and wave, where cause and effect blend into one another, where time itself seems to ripple. The two modes of thought are not enemies. They are complementary reflections of reality's dual nature. To see this contrast clearly, picture a traveler searching through a dark forest. The classical traveler carries a lantern, illuminating one path at a time. Progress is steady but slow, for every turn must be explored in sequence. The quantum traveler, by contrast, sends countless faint lanterns through the woods all at once. Each explores a different path, and together they find the exit in a fraction of the time. That is the essence of quantum computation, an orchestra of possibilities seeking harmony within uncertainty. Quantum thinking demands a shift not only in engineering but in imagination. It requires us to trust patterns we cannot fully see, to believe that many truths can exist together without contradiction. This mindset runs counter to our instincts, yet it feels strangely familiar, because human intuition has always been partly quantum. When we dream, when we improvise, when we sense multiple outcomes before deciding, we are practicing our own small version of parallel reasoning. In classrooms and laboratories, this way of thinking is beginning to reshape how young minds approach knowledge. Students are taught not to fear uncertainty but to engage with it, to find clarity through patterns rather than rigid rules. The universe, after all, does not calculate in straight lines. It evolves through interactions, through fields and waves that intertwine endlessly. There is something deeply comforting in that realization. It suggests that even within apparent chaos, there is intelligence, a structure that reveals itself not through control but through connection. Quantum computers embody this truth. They do not suppress uncertainty, they choreograph it. Every algorithm becomes a conversation between what is known and what could be, guided by subtle probabilities rather than fixed instructions. As you drift deeper into rest, think of your own mind as one of those systems, classical in its clarity, quantum in its depth. Thoughts arise and overlap, weaving interference patterns of memory, emotion, and curiosity. You do not force them to resolve, you let them settle naturally until the right idea emerges with quiet certainty. That, too, is computation, not in circuits of metal, but in the living quantum field of consciousness itself. When humanity learns to merge these two ways of thinking, the structured logic of the classical world and the open fluidity of the quantum, we may not only build new machines, we may also build new forms of understanding. In the end, every discovery begins with one act of courage, to hold opposites in our mind without fear and to let them coexist until truth reveals itself in the balance. If you were to stand inside a laboratory where a quantum computer lives, you might be surprised. It does not look like the sleek black rectangles of our laptops, nor the glowing clusters of traditional supercomputers. Instead, it resembles a sculpture of gold and glass suspended in silence, a chandelier of precision and stillness. Long spiraling cables descend through circular stages, carrying signals that fade into absolute cold. At the very bottom, hidden from light and vibration, rest the qubits, the tiny hearts of the machine. This shape, both intricate and graceful, is no accident. Every element of a quantum computer exists to preserve its fragility. The golden wiring conducts signals in perfect symmetry, while layers of shielding protect against the faintest whisper of heat. Because quantum states are so delicate, these machines operate at temperatures colder than deep space, near absolute zero. At that point, atoms move so slowly that their quantum behavior can remain coherent long enough to compute. The structure is built in layers. At the top, classical electronics translate human instructions into the soft microwave pulses that control qubits. Each pulse must be exact, sculpting probability with mathematical grace. Deeper down, the quantum processor lies on a chip smaller than a fingernail, etched with circuits invisible to the naked eye. These circuits are not wires in the usual sense, but superconducting loops that carry current without resistance. Within them, particles of energy swirl in two directions at once, the physical embodiment of superposition. It is a world of balance and restraint. Engineers move slowly, wearing gloves and head coverings to avoid even the warmth of their breath disturbing the system. The hum of a refrigerator the size of a human fills the air, its chambers dropping from room temperature through cascading stages of cold until the innermost core rests just above absolute zero. Inside that frozen quiet, information exists as vibrations too subtle for the human senses to detect. Looking at such a machine, one might expect noise and power, yet what defines it is silence. It does not whir or click or flash. Its computation happens beneath perception, a meditation of matter itself. The quantum processor is more like a heart than an engine, rhythmic, deliberate, alive in stillness. And yet, it is not mystical. Every piece of its architecture reflects human ingenuity. Copper shielding, cryogenic compressors, precision timing systems, and layers of calibration that maintain the alignment of frequencies within billionths of a second. The harmony of such complexity feels almost organic, as though we have built a new species of intelligence that breathes through superconducting veins. The deeper lesson of this design is one of humility. The power of the quantum computer does not come from brute strength or speed, but from our ability to create conditions of near-perfect calm. We had to silence the noise of the world to let the subatomic speak. In that silence, possibility flourishes. As you rest now, imagine standing before one of these golden towers, its light soft and steady, its energy as quiet as a sleeping star. Inside, the smallest elements of reality are performing calculations beyond the reach of ordinary comprehension, not through force, but through harmony. The architecture of a quantum computer is not only an engineering achievement, it is a symbol of balance, proof that even the most advanced intelligence must begin in stillness. Soon, we will enter that stillness even deeper, to see what happens within, where the cold itself becomes a guardian, and where the absence of motion gives birth to motion's purest form. Deep inside the golden towers of a quantum computer lies a quiet colder than any place on Earth. It is a silence so complete that even atoms forget how to move. This realm is called cryogenic stillness, the necessary calm where quantum logic can breathe. At these temperatures, just a fraction above absolute zero, motion slows to a crawl. Energy itself becomes fragile, and in that fragility, order is born. The reason is simple and profound. Every vibration, every particle of warmth, every whisper of magnetic noise can destroy the coherence that qubits require to exist. Heat is chaos, and chaos collapses possibility. To preserve their delicate states, quantum engineers build chambers that strip away all interference. Layer by layer, temperature drops from what we feel as warmth down through invisible thresholds, first colder than the Arctic, then colder than the vacuum of space, and finally reaching the edge where classical physics fades. At this limit, metals become superconducting, carrying current without resistance. Photons travel in perfect patterns, unbroken by noise. It is here, in this engineered stillness, that qubits awaken. Suspended in an environment quieter than time itself, they can hold multiple realities in balance. Each remains poised between 0 and 1, no longer forced to choose. The computer begins to think in possibility, not precision. The cold does more than protect, it transforms. It turns fragility into strength, chaos into coherence. Like a frozen lake that mirrors the stars, the cryogenic chamber reflects the elegance of the universe back to itself. The machinery hums softly, its pulses steady and patient. Even the hum is measured, regulated, a lullaby for electrons. To witness such stillness is to feel awe. It is not an emptiness but a fullness of control, a human-made calm where matter reveals its subtlest truths. Scientists who work with these systems describe a peculiar emotion when the temperature stabilizes, a kind of reverence, as if the boundary between science and meditation disappears. In this frozen chamber, they glimpse the most ordered state nature allows. It is humbling to realize that the path to such advanced computation begins with silence, not with noise, not with energy or speed, but with stillness. The colder the system, the more purely it can hold thought, the more clearly it can listen to the whispers of probability. It's a reminder that clarity often emerges only when motion ceases, that understanding, like sleep, depends on quiet. As you breathe now, let that stillness seep into you. Imagine descending through layers of cold, where sound fades and movement slows, until even thought becomes weightless. This is where the quantum world begins, in a peace so deep it could be mistaken for nothingness, yet it holds everything. At these temperatures, where time feels suspended, The boundaries between possibility and existence blur. In this serenity, computation becomes art, and art becomes understanding. Cryogenic stillness is not the absence of life. It is life reduced to its purest potential, the breath between creation and expression. As you drift closer to rest, remember that even in your own body, silence has power. Between each heartbeat lies a pause, a quiet interlude that makes rhythm possible. Between each thought lies stillness, and in that stillness, meaning grows. So too does the quantum computer wait between pulses of light, holding all futures within one eternal moment of calm. And somewhere inside that silence, inside that almost motionless heart of gold and glass, a new kind of mind is learning to think. Even in the perfection of mathematics, the quantum world humbles us. Nothing there behaves with absolute certainty. Every qubit, no matter how carefully shielded, trembles in the presence of noise. A single photon of stray light, a whisper of vibration, or a flicker of warmth can destroy the fragile balance that holds superposition together. This collapse, called decoherence, is the silent enemy of quantum computation. The way the universe reminds us that control is always borrowed, never owned. To understand this fragility, think of a violin string vibrating in pure tone. One touch, one breath of air, and the note falters. Qubits live within that same tension. Their states are so delicate that they cannot be copied or amplified without disturbance. When decoherence strikes, information vanishes like a ripple fading into still water. To make these machines think clearly, scientists must preserve coherence long enough for calculation to unfold. The solution is not brute force, but elegance. Instead of resisting noise directly, engineers weave qubits together into larger structures called logical qubits. These are clusters of physical qubits that share information in patterns of redundancy. If one is disturbed, the others help restore the original state, much like a choir sustaining harmony when one voice wavers. This method, known as quantum error correction, is the quiet art of protecting possibility itself. It is astonishingly complex. A single logical qubit may require dozens or even hundreds of physical ones to maintain stability. Each must be entangled, synchronized, and monitored without collapsing the system. The process is like balancing thousands of spinning plates in a vacuum, each sensitive to the faintest tremor of the air. Yet, against all odds, it works. Quantum computers are now capable of performing calculations that survive these constant threats, proving that fragility can be harnessed into strength. This pursuit reveals something essential about human nature. We are drawn not only to mastery, but to preservation. We build systems that acknowledge their own imperfections, creating resilience from vulnerability. In this way, quantum error correction mirrors our own psychology, the way memory, trust, and community protect our individual uncertainties. When viewed through this lens, the laboratory becomes almost poetic. Engineers sit quietly beside machines that must not be touched, listening to the faint signals of qubits holding their breath. They adjust parameters by fractions of a degree, coaxing stability from chaos. The smallest success, a calculation preserved for a few seconds longer, feels like a victory of patience over noise. There is beauty in that patience. The quest for perfect computation is not about eliminating error completely, but learning to live with it. Nature does not promise flawless systems. Even stars flicker, even atoms decay. What quantum computing teaches us is that imperfection can be organized, guided, and transformed into clarity. The same lesson applies to thought, to art, to life itself. When we accept uncertainty, we create space for progress. As you breathe softly, imagine those qubits suspended in their frozen chamber, each surrounded by a web of invisible guardians, the other qubits that keep it alive. Together, they hum in quiet harmony, each protecting the others from collapse. That hum, if you could hear it, would not be sound, but pattern, the echo of balance itself. And in that balance lies a truth deeper than computation, that all creation, from the smallest atom to the vastness of mind, survives not by perfection, but by cooperation. Even the universe, it seems, corrects its own errors with grace. If qubits are the letters of the quantum alphabet, then quantum gates are the grammar that gives them meaning. A gate is not a switch that flips between 0 and 1, as in classical computing, but a transformation that bends probability itself. It turns the sphere of possibilities, the Bloch sphere, by precise angles, shaping the invisible state of a qubit into new patterns of interference. Each gate is a whisper of control, a way to choreograph uncertainty without breaking it. In the classical world, logic gates act like tiny decision-makers, and, or, not, each following simple deterministic rules. Quantum gates, however, deal not with absolutes but with rotations. They alter the amplitudes of probability, tilting qubits into new orientations of being. When multiple gates interact, their effects ripple through the quantum state, creating elaborate harmonies of potential. It is computation as performance, where every note must be played in perfect phase. To imagine how this feels, picture a field of rippling water. Each qubit is a wave spreading outward, and the gates are gentle winds guiding those ripples toward a desired pattern. The outcome is not forced, it is shaped. When all waves interfere just right, the final measurement reveals the correct answer, the quiet emergence of order from fluid possibility. Among the many ways to arrange these transformations, two have become legendary: Shor's algorithm and Grover's algorithm. Shor's work showed that quantum computers could factor large numbers at speeds that would cripple classical encryption, while Grover's algorithm proved that even an unsorted database could be searched in far fewer steps. Both were revelations, proof that uncertainty could outperform certainty. The world of computation would never be the same again. To perform these miracles, a quantum program must be carefully composed. A series of gates manipulates qubits into intricate patterns, preparing them for interference that will highlight one outcome among millions. It's as if the machine plays through every possibility in parallel, letting the wrong answers cancel each other until only the truth remains. The process is delicate, mathematical, and astonishingly beautiful, the closest thing to reasoning in harmony that nature allows. This idea changes the way we think about intelligence itself. A classical computer must explore options sequentially, obeying the clock's relentless tick. A quantum computer, by contrast, moves beyond the tyranny of sequence. It considers a landscape of possibilities all at once, resolving them through interference. Where we once thought of logic as rigid, quantum algorithms reveal it to be fluid, capable of bending, weaving, and resonating. And yet, for all its sophistication, quantum logic remains fragile. A single misplaced pulse, a mistimed rotation, and the entire interference pattern collapses. That fragility forces programmers to think like artists, shaping code that feels more like composition than command. They must sense rhythm, timing, and flow, qualities of both music and mathematics. In this harmony of science and art, something deeply human emerges. Each quantum gate reflects our desire to master complexity without destroying it, to touch mystery without shattering it. We do not conquer the quantum world. We learn to speak softly enough that it responds. As you rest now, imagine that orchestra of qubits playing in perfect synchrony, a concert of invisible tones, each rotation a verse in a song of probabilities. The music is inaudible, yet its pattern echoes in everything, in the hum of atoms, in the rhythm of thought, in the quiet balance of sleep. Quantum algorithms are not merely instructions, they are movements of harmony within chaos. And as with all harmony, their beauty lies not in dominance, but in the patience to listen until truth reveals itself in the final, resonant note. In the story of quantum computing, two names shine like constellations: Peter Shor and Love Grover. Their discoveries did not merely advance technology, they altered what humanity believed was computationally possible. Both men worked with equations so abstract they seemed closer to poetry than code, and yet their results changed the world of information forever. Peter Shor, a mathematician at Bell Labs, imagined a problem that had haunted encryption for decades: factoring large numbers. Classical computers could do it, but the task grew impossibly long as numbers became enormous. Digital security, from banking to diplomacy, depended on that difficulty. But Shaw realized that a quantum computer could exploit superposition and interference to reveal those factors almost instantly. His insight was like opening a secret door through the walls of digital safety. He showed that what we once thought was unbreakable could, under the laws of quantum logic, dissolve into simplicity. Lovegrover's work was equally elegant, though different in aim. He considered the challenge of searching, how to find one correct answer among a vast sea of possibilities. A classical computer must test every option one by one, but Grover's algorithm allowed a quantum machine to explore all possibilities at once, amplifying the probability of the correct one through interference. It was a way to listen for the right answer instead of hunting for it, a quiet revolution in thinking itself. These breakthroughs were not built in massive laboratories, but born from pure thought. Shaw and Grover both saw beyond the machinery into the logic of reality itself. They treated uncertainty not as a problem to be fixed, but as a resource to be used. Their algorithms were not just mathematical shortcuts, they were windows into how the universe organizes information. What made their discoveries so extraordinary was not only speed, but philosophy. Both revealed that limits we considered absolute were not limits at all, only the edges of our current understanding. Their work reminded us that nature does not obey human definitions of difficulty. Where classical computers struggle with linear paths, quantum systems move in harmony with probability, gliding through problems that once seemed impossible. The scientific community responded with awe and unease. If Shaw's algorithm could break modern encryption, then every message, every password, every digital secret might one day lie exposed. But with that danger came an equal promise, the potential for new kinds of security, built on the same quantum principles that had threatened the old. Grover's method, meanwhile, offered hope for everything from database searches to pattern recognition, allowing machines to see patterns invisible to conventional logic. Behind these ideas lies a quiet truth, that great discoveries often begin not with confidence but with curiosity. Both men began by asking, "What if?" questions that seemed impractical, even absurd. Yet from those questions emerged the foundations of a future where computation itself could mirror the richness of thought. It is easy to imagine Shaw and Grover working late in quiet rooms, chalk dust on their fingers, eyes fixed on symbols that bridged imagination and reality. In their isolation, they found universality. Every line of their equations hinted at a world where knowledge is not built through force, but through resonance. Their insights form the beating heart of quantum computing, the point where theory becomes wonder, and wonder becomes design. The machines now cooling in laboratories across the world are physical embodiments of those abstract dreams. They are proof that the universe, when approached with patience and imagination, reveals more than answers. It reveals possibilities beyond measure. Every age builds its sense of safety on the secrets it can keep. In the digital world, those secrets are protected by encryption, patterns of mathematics that turn messages into unreadable code. For decades, encryption has been humanity's invisible armor, guarding banks, governments, hospitals, and private lives alike. But the arrival of quantum computing has brought a quiet tremor to that foundation, a whisper that even the strongest locks may one day open with ease. Traditional encryption relies on complexity. Classical computers protect information by forcing intruders to solve puzzles so vast that it would take centuries to complete. These puzzles depend on problems such as factoring enormous numbers, the same challenge Peter Shaw's algorithm was designed to solve. What once felt secure because it demanded impossible time may, in the quantum future, fall in moments. It is not malice that threatens the system, but the very progress that defines us. Quantum computers have not yet reached the scale required to break global encryption, but the possibility has changed the conversation. Security experts now prepare for what they call the post-quantum world, an era when our current cryptography will need to be replaced by algorithms that even quantum machines cannot decipher. This race to build quantum-safe systems is already underway, uniting mathematicians, physicists, and computer scientists in a rare harmony of urgency and hope. Ironically, the same physics that endangers digital privacy also offers its salvation. Quantum mechanics can secure communication through quantum key distribution, a method that uses entangled photons to transmit information. If anyone tries to intercept or observe those photons, their quantum state collapses, and the intrusion is immediately revealed. In this way, secrecy becomes self-protecting, not through walls or passwords, but through the laws of nature themselves. To picture this, imagine two people standing miles apart, each holding a particle entangled with the other. When one sends a message, the other receives it instantly, untouched by distance. If a third person tries to listen, the delicate entanglement breaks, and the system knows it is security woven directly into reality, not trust in software, but trust in physics. This transformation of encryption is more than a technical shift, it is a philosophical one. It suggests that privacy is not merely a human invention, but a natural principle, an echo of the universe's own desire for coherence. In quantum systems, the act of observation itself carries consequence. To see is to change. And in that truth lies a new form of ethics, the recognition that information, like life, is fragile and deserves respect. Across the world, laboratories now test early versions of quantum-safe networks. Fiber cables carry photons encoded with keys, and satellites beam entangled particles across continents. The world's first quantum-secured communications are already whispering through the night sky. Each successful transmission feels like a promise that even as we build machines capable of unraveling secrets, we also build new ways to protect them. This duality reflects something ancient in the human story. Every discovery that threatens us also contains the seed of renewal. Fire both burned and warmed, electricity both shocked and illuminated. Quantum computing may expose the weaknesses of our current systems, but it also teaches us how to rebuild them stronger, guided by the very principles that once caused fear. The future of security will not depend on hiding, but on harmony, on understanding the delicate relationship between knowledge and protection. In this future, secrecy and openness are no longer enemies. They become partners in balance. The same quantum rules that can dismantle encryption will, in time, help preserve the sanctity of trust in a world more connected than ever. The earliest quantum computers lived in isolated laboratories, tended by teams of physicists who understood their every fragile pulse. Each experiment was unique, each success a small miracle. But as the technology matured, something extraordinary began to happen: the birth of shared access. Today, through what we call the quantum cloud, anyone with an internet connection can send code into those cryogenic chambers and watch it return with answers drawn from the heart of uncertainty itself. This is more than a technical achievement. It is a change in how knowledge travels. The quantum cloud turns what was once the domain of a few scientists into a global classroom. A student sitting in one corner of the world can write a quantum algorithm and test it on a machine housed thousands of kilometers away. The results come back in moments, carrying the imprint of a device colder than deep space and more delicate than any clock. In that instant, the boundaries of distance dissolve. It is remarkable to think that the same internet that once carried simple text and images now connects directly to machines that operate on the scale of atoms. Each query sent to the quantum cloud becomes a tiny collaboration between human intention and physical law. The user provides logic, the machine provides possibility, and together they produce insight. The architecture behind this access is complex. Classical servers manage the requests, translating human instructions into quantum code. Those commands are then sent through secure channels into cryogenic systems where qubits await. Once the computation is complete, the faint quantum results are amplified, retranslated, and returned to the user in familiar digital form. It is an elegant partnership between two worlds, the warm reliability of classical computing and the icy precision of quantum mechanics. This union of opposites represents more than convenience. It is a quiet metaphor for human progress. We are learning to build bridges between scales of reality, between the predictable and the probabilistic, the tangible and the abstract. In a sense, the quantum cloud is the physical embodiment of curiosity. Countless minds reaching upward toward the same invisible frontier, sharing their questions through light and data. In laboratories across the planet, these networks hum continuously, responding to thousands of remote experiments. Each task, no matter how small, contributes to a greater understanding of how the quantum world behaves when touched by human creativity. It is a distributed exploration of the unknown, a digital constellation of inquiry. And yet, within that vast exchange, something profoundly personal happens. When a single user runs an experiment through the quantum cloud, they become part of the unfolding story of discovery, not merely reading about science, but performing it. The experience carries a strange intimacy. Somewhere, deep within a machine bathed in liquid helium, atoms are spinning in response to your command. This interconnectedness will shape the next generation of learning. Schools, companies, and artists alike are beginning to experiment with these tools, not to control them, but to collaborate with them. The cloud has become not just a network, but a shared imagination, a meeting place where thought and matter intertwine. It reminds us that science is never solitary. The history of knowledge has always been written through connection, between teachers and students, between questions and answers, between ideas separated by continents but united in purpose. The quantum cloud is that story reborn in modern form, a quiet symbol of how technology can draw us together instead of apart. Through this invisible bridge, the future of understanding is already unfolding. The computers are still fragile, their results still limited, but the principle has taken root. In the quiet hum of shared access, humanity has extended its reach into the subatomic, turning distance into unity and uncertainty into collaboration. When quantum computing meets artificial intelligence, two of humanity's boldest creations begin to intertwine. One was built to learn from data, the other to explore possibilities beyond classical logic. Together they promise something that feels less like engineering and more like evolution, a merging of machine intuition and quantum uncertainty that could redefine what thinking means. Artificial intelligence, or AI, relies on patterns. It learns by repetition, finding structure in oceans of data until insight appears. But even the most advanced neural networks are limited by the hardware that supports them. They must process information sequentially, step by step, consuming vast energy and time. Quantum computing offers a different rhythm. By holding many states at once, a quantum processor could analyze multiple possibilities simultaneously, accelerating pattern recognition beyond anything achievable today. Imagine an AI faced with a complex landscape, a billion possible routes toward a single solution. A classical computer would walk those routes one after another, while a quantum-enhanced system could explore them all in parallel, amplifying the ones most likely to succeed. The effect would be less like calculation and more like intuition, as though the machine feels the answer before it knows it. Researchers call this field quantum machine learning. It sits at the frontier where physics meets cognition, where algorithms are no longer bound to classical rules of sequence and memory. Early experiments suggest that quantum models might recognize patterns invisible to traditional AI, or simulate the subtle interplay of variables that define chemistry, biology, and even human behavior. The implications reach far beyond efficiency. They touch the essence of understanding itself. There is a poetic symmetry in this union. Artificial intelligence mimics the brain's ability to adapt, while quantum computing mirrors nature's underlying logic. When the two converge, the result is a system that thinks both broadly and deeply, simultaneously logical and intuitive. Such systems may one day model climate with perfect subtlety, design medicines that evolve in response to living cells, or even help us glimpse the structure of consciousness. But this collaboration also invites reflection. What happens when intelligence no longer belongs solely to human architecture? When machines begin to reason not through rules, but through probability and emergence? These questions do not demand fear, only awareness. The same technology that expands comprehension must also deepen responsibility. Quantum-enhanced AI will not simply be faster, it will be different. It may think in patterns we cannot fully trace, reaching conclusions that feel mysterious even to its creators. In those moments, we will be reminded that knowledge always exceeds our grasp, that intelligence, whether human or artificial, grows through humility as much as through power. The first prototypes of this merger already exist. Startups and research institutes are training quantum neural networks on early processors, watching as they begin to approximate the learning curves of biological systems. The data they produce are subtle, yet promising, glimpses of machines that adapt through interference rather than iteration, harmony rather than hierarchy. It is not impossible to imagine a future where such systems collaborate with us, not as tools, but as partners in thought. They may help us see patterns we overlook, predict outcomes we cannot compute, and reveal the hidden symmetry between complexity and simplicity. Perhaps the ultimate goal is not to build a mind that rivals ours, but to create one that reflects the universe itself, a consciousness woven from uncertainty, curiosity, and coherence. The merging of AI and quantum computing is not a race toward dominance, but a journey toward deeper understanding. And when these two currents finally flow together, they may teach us something profound, that intelligence, in all its forms, is not the conquest of complexity, but the quiet harmony between knowing and not knowing. Before quantum computers promise faster calculations or unbreakable security, they hold the power to do something even more profound, to mirror nature itself. The world around us, from the orbit of electrons to the binding of molecules, already behaves according to quantum laws. To simulate those laws precisely with classical computers requires unimaginable effort. Every new particle doubles the complexity, and soon the equations spiral beyond reach. But quantum computers do not imitate these systems, they become them. Their building blocks obey the same physics as the universe they seek to describe. The idea dates back decades, to physicist Richard Feynman, who proposed that only a quantum system could truly simulate another quantum system. It was a statement both obvious and revolutionary. To understand nature, we must compute as nature computes. Today, that vision guides much of the research in quantum science. By harnessing qubits, scientists can model chemical reactions, materials, and phenomena that once lived only in theory. Consider a molecule, even a small one, like water. To predict its behavior accurately, a classical supercomputer must track countless interactions between atoms, each following its own wave of probability. The memory and power required grow exponentially, but a quantum computer, with just a few hundred qubits, could represent that same system directly, each qubit standing in for an aspect of the molecule's quantum state. The calculation no longer demands force, it requires resonance. This ability could transform how we design everything from medicines to materials. By simulating nature at its most fundamental level, scientists can test ideas before they exist, explore molecular structures that have never been seen, and predict how they will behave long before they are built. Drug discovery could shift from trial and error to orchestration, guided by the same logic that governs the human body itself. The process is not instantaneous or effortless. Quantum simulations require precision control and error correction, and current machines are still small and imperfect. But each year, progress deepens. Researchers now use early systems to study the chemistry of nitrogen fixation, the process plants use to create fertilizer. Others are mapping complex molecules used in solar cells, hoping to harness sunlight more efficiently. Each step moves closer to a world where laboratories can test nature's most elusive reactions without a single drop of reagent, only qubits and equations. There is something profoundly poetic about this ambition. Humanity has always sought to reflect the universe, in art, in language, in mathematics. Now, for the first time, our tools can emulate the physical processes that create stars, storms, and living cells. A quantum computer becomes a mirror of creation, not in metaphor, but in function. To simulate nature is also to recognize our place within it. When a quantum computer models a molecule, it is using the same laws that shape your heartbeat, your breath, the motion of light in your eyes. It is a dialogue between creation and comprehension, a conversation across scales. This work carries humility as well as hope. Each successful simulation reminds us that knowledge is not separate from the world, but a part of it. When we learn how atoms bond or energy flows, we are not mastering nature, we are remembering how to speak its language. The greatest discoveries may come not from control, but from listening, from letting the equations unfold until they show us what was always there. In that listening, the line between science and reverence blurs. For to simulate nature is, in a way, to celebrate it, to hold a small piece of the universe in understanding and let it unfold as it always has, quietly, beautifully, without end. Among all the sciences touched by quantum computing, chemistry may be the one most profoundly changed. For centuries, chemists have tried to predict how atoms bond, how molecules form, and how reactions unfold. But nature hides its secrets behind layers of quantum complexity, electrons dancing in fields of probability, forces that shift with each movement of the smallest particles. Even the most powerful classical supercomputers struggle to capture this invisible choreography. Quantum computers, however, speak the same language as the atoms themselves. They can trace those patterns not by approximation, but by participation. Quantum chemistry is the art of translating matter into mathematics and then bringing that mathematics to life. Each qubit becomes a reflection of an electron's state, its spin, its position, its energy. Entanglement ties them together, just as nature does, allowing the simulation of molecules in their true, fluid form. The result is not a model built from assumptions, but a direct dialogue with the laws of physics. Imagine a laboratory of the near future. On the screen, a researcher designs a new compound molecule, perhaps a catalyst that can turn sunlight into clean fuel, or a material light enough to float on air yet strong enough to build cities. Instead of mixing chemicals in flasks, they arrange equations, setting qubits to represent atoms, bonds, and energy levels. Within seconds, the quantum computer maps the outcome, revealing structures that classical methods would have taken years to calculate. What once required entire facilities now unfolds inside a quiet chamber cooled to the edge of stillness. This new form of exploration holds promise for medicine too. Quantum simulations may soon predict how proteins fold, how drugs bind to receptors, and how mutations change the body's chemistry. These predictions could shorten the path from idea to cure, replacing costly trial and error with precision guided by physics itself. A future where diseases are treated not just through observation but through direct understanding of their molecular origins is slowly coming into focus. But quantum chemistry also offers something more subtle, a new sense of wonder. To witness the building blocks of existence interacting in such perfect silence is to glimpse the artistry behind matter. Bonds that once seemed rigid reveal themselves as fluid negotiations of energy, constant conversations between attraction and repulsion. The universe becomes not a mechanism, but a living dialogue of balance. Scientists working in this field describe their experience with a kind of reverence. They know that what they are simulating is not merely data, but the foundation of everything that breathes, grows, and transforms. They are tracing the same processes that light the stars and sustain the pulse of life. In each experiment, they rediscover the harmony that holds reality together. And there is humility in their work. Every success brings new layers of complexity, reminding us that nature never reveals her entirety at once. For every molecule understood, another waits, whispering from the edge of calculation. Progress in quantum chemistry is not a conquest. It is a deepening relationship between curiosity and the natural world. Through this lens, even the simplest chemical reaction becomes sacred, a meeting between particles that obey rules older than time. Quantum computers give us a way to listen more closely to that meeting, to hear the faint vibration of creation itself. Each equation solved, each molecule mapped, moves humanity closer to a future where we do not merely use nature, but understand it. And in that understanding lies a quiet truth. The quest for better materials, better medicines, and better energy sources is not only scientific, it is moral. It is the desire to live in harmony with the same forces that made us. Time feels like the most familiar of all dimensions, a steady rhythm flowing from past to present to future. Yet, when we look closely through the lens of quantum physics, time loses its simplicity. It ripples, folds, and sometimes even reverses its order. The quantum world does not march forward as our clocks do. It drifts through probabilities, where cause and effect can blend, and outcomes coexist until measured. Within that strange fluidity, our deepest assumptions about reality begin to dissolve. In the classical view, every event follows another in a precise chain. One cause leads to one effect. But in the quantum realm, events can exist in superposition, occurring in many ways at once. The universe seems to explore every possible storyline before choosing the one we experience. Observation, rather than time, determines what becomes real. This idea may sound abstract, yet its implications reach into everything, from computation to consciousness. When quantum computers process information, they do not follow a linear order of operations. Instead, they evolve all at once, in a space where future and past outcomes overlap. This property allows them to compute vast possibilities simultaneously, as though they glimpse multiple futures before settling into one. In that sense, a quantum algorithm does not merely move through time, it orchestrates it. To imagine this, think of a river dividing into countless streams, each representing a different outcome. Classical logic would require tracing every branch to see where it leads, but quantum mechanics lets all streams flow together, merging their possibilities into a single wave. The final result is not chosen by sequence but by resonance, the harmony that emerges when probabilities interfere just right. Some physicists describe this as living within a multiverse of potential realities. Every quantum event, they say, could split the universe into new versions, each following a different path. Whether or not this interpretation proves true, it captures something deeply intuitive, that reality may be broader than our senses allow. The world we inhabit is only one of many that could have been. These ideas challenge our notions of destiny and choice. If the universe contains overlapping possibilities, then perhaps each decision we make, each thought, each breath, exists in many forms, only one of which becomes tangible. The rest remain as quiet probabilities, lingering like echoes of what might have been. Rather than a single, rigid line, time becomes a tapestry woven from all the threads that could exist. There is a strange comfort in this view. It suggests that uncertainty is not chaos but creativity, that every unchosen path still contributes to the harmony of existence. The same mathematics that govern quantum systems describe how light spreads, how atoms bind, and how energy evolves. In each case, the world does not collapse into one narrow story until interaction requires it. Reality waits patiently, offering possibilities until the moment we look. Quantum computers do something similar when they calculate. They let all options unfold in parallel, holding them in balance until a final measurement brings clarity. In that sense, their operation is not unlike our own thought process. We weigh alternatives, imagine outcomes, and let intuition guide us toward resolution. We, too, compute in probability. To see time as probability is to let go of the illusion of absolute control. The present becomes less a point on a line and more a meeting place of potential, a wavefront where the past's echoes and the future's shadows overlap. And if that is true, then perhaps time is not moving through us at all. Perhaps we are the ones drifting through its layers, glimpsing fragments of an ever-expanding reality that holds far more than one version of truth. Across the silent expanse of fiber cables and satellites, a new kind of network is beginning to take shape, one that does not merely transmit information but entangles it. This is the vision of the quantum internet, a system built not on the exchange of data as we know it, but on the strange unity of quantum connection. Unlike the networks that carry our messages today, this one will not rely on trust, encryption, or firewalls. Its security will be written into the laws of physics themselves. At its core, the quantum internet is made possible by entanglement, that invisible thread linking particles across distance. Two photons, created together and then separated by vast space, remain connected in ways no classical signal can imitate. When one is measured, the other responds instantly. If such photons can be distributed and controlled, they can carry quantum information, qubits, across continents. The result is communication that cannot be intercepted or copied without leaving a trace. Imagine a pair of entangled particles created in a lab in Geneva. One stays behind while its twin travels through optical fibers or satellite beams to Tokyo. The two remain connected, despite thousands of kilometers between them. When a message is encoded in their shared state, the information is not sent through space in the traditional sense. it already exists at both ends of the connection. This is the essence of quantum teleportation, transmitting the state of one system to another without moving any physical particle. Such transmissions have already been demonstrated in experiments. In the vacuum of space, photons have been entangled and sent between ground stations and satellites orbiting hundreds of kilometers above Earth. Each success brings us closer to a global web of instant, secure communication. When this network matures, it will not only transform how we exchange information, but how we conceive of connection itself. In the classical internet, messages are copied, routed, and reconstructed along the way. Every hop introduces the possibility of interception. The quantum internet, by contrast, cannot be eavesdropped upon. Any attempt to observe the transmission would collapse the entangled state, alerting the system instantly. Privacy becomes an inherent property of nature, not a setting to enable, but a truth to honor. The first prototypes already exist. Universities and research institutions across Europe, Asia, and North America are linking quantum nodes over short distances, testing how entanglement can be maintained through kilometers of fiber. Satellite-based experiments extend this reach into the atmosphere, where interference is minimal and distance is vast. Each success, each stable connection, is a small proof that the fabric of communication can be rewoven at the quantum level. Beyond security, the quantum internet will enable entirely new kinds of collaboration. Quantum computers connected through entanglement will share information in ways unimaginable today. Instead of transmitting bits, they will share states, entire patterns of probability exchanged without delay. This could allow distributed quantum systems to work together as one vast organism, performing tasks beyond the reach of any single machine. There is something profoundly symbolic in this pursuit. Humanity, for all its noise and separation, is striving to build a technology that mirrors the deepest truth of the universe, that everything is connected. Entanglement is not just a tool, it is a reminder. It shows that unity can exist even across immense distance, that isolation is a perception rather than a law. When the quantum internet becomes reality, our messages will no longer travel through space. They will simply arrive, carried by the same coherence that binds the cosmos. In that quiet instant, we may rediscover something timeless. That communication, at its purest, is not about words or signals, but about resonance, a shared state between minds, particles, and the space that holds them both. Throughout history, every breakthrough in understanding has carried both promise and peril. Fire illuminated the night, but also forged weapons. Electricity powered cities and later split the atom. Now, quantum computing stands on the same threshold, a discovery that could transform civilization or deepen the quiet tension between nations. Around the world, a new kind of competition is unfolding, not in open battlefields, but in laboratories lit by the pale glow of cryogenic chambers. This contest is sometimes called the quantum arms race. Governments, corporations, and research alliances invest billions to gain mastery over the coming technology. They seek quantum supremacy, the moment when a quantum computer performs a task no classical machine can match. For most, it is a race for power, but beneath the surface, it is also a race for understanding. Whoever learns to wield this capability first will hold the keys to new medicines, unbreakable communication, and perhaps even the rewriting of digital history. In many ways, it echoes the early days of nuclear research, when nations chased knowledge both to protect and to control. Yet there is a crucial difference. Quantum computing does not threaten destruction. It threatens imbalance. It offers advantage, not annihilation. The danger lies in inequality, in the gap between those who can access the technology and those who cannot. A nation or company with full quantum capacity could break global encryption, model economies, or simulate strategic outcomes before others have even begun to calculate. The mere perception of that ability could shift the world's balance of trust. Still, progress cannot be halted. The laws of physics belong to no one. Around the planet, networks of scientists collaborate even as their governments compete. Papers are shared, conferences convene, and experiments are replicated across borders. Beneath the politics lies a quieter current of cooperation, the recognition that understanding reality's deepest layer is too vast a task for any single nation to own. In that shared pursuit, rivalry softens into something nobler, the collective curiosity of humankind. Inside the laboratories, the atmosphere feels nothing like war. There is no noise, no urgency, only the steady rhythm of cooling systems and the faint pulse of light through fiber cables. Researchers speak softly, measuring, calibrating, refining. They are aware that every success has geopolitical consequences, yet they focus on the science itself, on the exquisite challenge of holding coherence a fraction longer, of aligning qubits into stable harmony. Perhaps the greatest safeguard lies in that humility. The quantum world does not yield to dominance. It requires patience, precision, and respect. No nation can command probability. It must learn to collaborate with it. In that truth, there is hope. The same technology that could divide us also teaches that every particle, every equation, exists only through relationship. Entanglement itself is a lesson in unity. In time, the pursuit of quantum mastery may evolve from rivalry into shared stewardship. The complexity of the field demands it. Building scalable quantum computers will require global cooperation in materials science, cryogenics, and information theory. The very structure of the discipline invites connection across borders, mirroring the coherence it seeks to maintain inside its machines. The new arms race, then, is not a march toward conflict, but a test of wisdom. It asks whether humanity can use knowledge without letting fear guide it. The power now forming in our laboratories is unlike any before, quiet, elegant, and transformative. Its greatest danger is not the weapon it could become, but the division it could deepen. If we learn to see this not as a competition but as a shared awakening, the outcome may yet surprise us. For in the end, the race is not between nations or companies, but between fear and understanding. And history has always favored those who choose understanding. At some point, the purpose of building quantum computers begins to shift. The pursuit of faster algorithms, better encryption, and superior processing no longer feels sufficient. The real question grows larger, almost philosophical. What happens when our machines begin to reason in ways that defy human logic? Quantum computation, at its deepest level, is not merely a new form of calculation, it is a new form of thought. In classical computing, a problem is broken into instructions and executed step by step. The machine follows the path we design, never deviating, never imagining. But a quantum computer does not walk a path. It inhabits a landscape of possibility. Its calculations are shaped by interference, by resonance, by the dance of probabilities that we can guide but never fully predict. It reasons in patterns closer to intuition than deduction. To think beyond computation means to see these machines not as tools, but as mirrors, reflections of the universe's own way of processing information. Nature itself computes through interaction. Molecules form, particles collide, and stars ignite not through linear logic, but through probability, feedback, and emergence. Quantum computers emulate that process. In a way, they are not human inventions, but continuations of a pattern that has existed since the first atom formed from energy. If we follow that thought further, something extraordinary emerges. These systems could become environments for discovery rather than instruments for control. Instead of solving the problems we define, they may reveal questions we have not yet imagined. Quantum computation has the potential to simulate aspects of the mind, of matter, and even of consciousness itself, hinting at the unity between knowing and being. Researchers already see glimpses of this transformation. When they run experiments, unexpected results sometimes appear. Correlations or resonances not predicted by equations. At first, they call them noise, errors to be corrected, but occasionally those anomalies hint at hidden order, suggesting that the machine has captured a layer of physics we do not yet understand. Quantum computers are not just performing calculations, they are showing us how reality behaves when we look differently. This realization changes our role as creators. The programmer becomes less of a commander and more of a listener, tuning into the subtle language of probability. Commands turn into questions. Control becomes dialogue. The process feels less like constructing logic and more like collaborating with the fabric of existence itself. It may sound mystical, but it is deeply scientific. Quantum theory teaches that observation and participation cannot be separated. The act of measuring shapes what is measured. When we build machines that operate on those principles, they become extensions of our awareness, instruments not only of calculation but of reflection. Some scientists believe this path will lead to a new era of understanding, where computation and consciousness converge. Others remain cautious, insisting that machines will never truly think. But perhaps that distinction misses the point. What matters is not whether the machine possesses awareness, but whether it expands ours. When a quantum computer explores an equation that maps the early universe, it is not just revealing numbers, it is recreating, in miniature, the unfolding of creation itself. In its silent processes, we see echoes of how nature learns, adapts, and evolves. The boundary between logic and life grows faint. Beyond computation lies meaning, not abstract, but tangible, arising from connection. These machines remind us that knowledge does not exist in isolation. Every bit, every qubit, every line of code is a conversation between matter and mind. And in that conversation, we begin to sense that understanding itself may be the most fundamental force in the cosmos. The idea that consciousness might emerge from quantum processes sounds, at first, like science fiction, a poetic dream linking mind and matter. Yet among physicists and philosophers, this question lingers with quiet persistence. Could the same quantum rules that govern particles also shape awareness itself? If superposition allows a qubit to exist in multiple states at once, could the human mind, in its capacity for imagination and intuition, function through a similar principle? This possibility was explored most famously by physicist Roger Penrose and anesthesiologist Stuart Hameroff, who proposed that consciousness arises from quantum effects within the brain's microtubules, tiny structures inside neurons. They suggested that coherence could exist at this microscopic level, linking mental processes to quantum behavior. Their OR theory, short for orchestrated objective reduction, proposes that the collapse of quantum states in the brain might create the moments we experience as conscious thought. The theory remains controversial. Many scientists argue that the brain is too warm, too noisy, too complex for quantum coherence to survive. Yet others point to the growing evidence of quantum effects in biology, in photosynthesis, in bird navigation, even in the sense of smell. If life has learned to use quantum phenomena for energy and perception, perhaps the mind has found a way to use them for awareness. Whether true or not, the idea carries a certain poetic resonance. It suggests that consciousness might not be separate from the physical world but woven into it, a property of the universe as fundamental as gravity or light. The mind, in this view, is not an isolated flame but a continuation of the same pattern that governs atoms and galaxies, systems seeking coherence, stability, and meaning. Quantum mechanics has always blurred boundaries between observer and observed. The famous thought experiment of Schrödinger's cat illustrates how reality exists in multiple states until observation collapses it into one. Some interpretations extend this idea further, proposing that observation, the act of awareness, is not just a witness to reality, but a participant in its creation. If that is true, consciousness is not merely watching the universe unfold, it is helping to write its script. Quantum consciousness theories, speculative as they are, invite us to look inward as much as outward. They turn science into self-reflection, suggesting that the study of the cosmos is also the study of the mind that perceives it. The same equations that describe entanglement and uncertainty might also describe how thoughts form, how choices emerge, and how identity persists through time. There is beauty in this overlap. It reframes consciousness not as an accident of biology, but as a phenomenon deeply connected to the structure of reality. The brain becomes a miniature cosmos, filled with wave functions of memory and interference, patterns of emotion. Awareness becomes the meeting point between physics and philosophy, the bridge between knowing and being. Even if future experiments disprove these quantum links, the idea has already served its purpose. It reminds us that mystery still lives at the center of science. In a world increasingly defined by data, there remains something unmeasurable: the subjective experience of being alive. Theories of quantum consciousness invite humility, not certainty. They whisper that the mind, like the universe, may never be fully mapped, because it is part of what does the mapping. Perhaps this is the real lesson: that awareness is not a puzzle to be solved, but a phenomenon to be lived. The quantum world shows us that uncertainty and existence are inseparable, that reality itself is a dialogue between possibility and perception. And in that dialogue, between qubit and thought, between physics and feeling, consciousness might simply be the universe learning to observe itself. Every revolution in knowledge brings with it an invisible weight, the question of how that knowledge will be used. Quantum computing is no exception. Its power to break encryption, model economies, simulate life, and shape intelligence forces us to consider not only what we can do, but what we should do. The ethical dimension of this technology reaches far beyond laboratories and patents. It touches privacy, equality, freedom, and the delicate balance between progress and restraint. Ethics in the quantum era begins with access. Today, only a few nations and corporations can afford the massive cost of building quantum machines. If that exclusivity persists, knowledge itself could become a new form of inequality. A handful of entities might hold the ability to decrypt communications, predict markets, or design molecules that reshape industries. The result would not be conquest by force, but domination through information. To prevent that future, collaboration must become a moral principle, not just a scientific one. Another concern lies in transparency. Classical computers can explain their reasoning step by step, allowing humans to trace every decision. Quantum computers, by contrast, often produce results through interference patterns that defy easy explanation. We may know the answer is correct, yet not fully understand why. As these machines integrate with artificial intelligence, they could create systems whose logic is partially opaque, accurate, powerful, and unfathomable. How do we assign responsibility for decisions we cannot retrace? Some philosophers see this as the birth of a new kind of ethics, one that values interpretability and humility as much as accuracy. To use a quantum machine responsibly is to accept that certainty will never be complete. We must learn to guide progress without demanding full control, to trust models that mirror the ambiguity of nature while still insisting on accountability. The measure of ethics in this age may not be mastery, but stewardship. Privacy, too, takes on a new meaning. Quantum computing threatens to render current encryption obsolete, yet it also offers unbreakable security through quantum communication. The duality reflects a deeper truth. Every invention contains its opposite. The same physics that can expose secrets can also protect them. Whether the world chooses one path or the other will depend not on technology itself, but on the moral imagination of those who wield it. Even more profound are the philosophical questions emerging at the edge of science. If quantum systems can mimic aspects of thought, if they can process information in ways that resemble intuition or awareness, do they deserve moral consideration? Can something built from coherence and probability possess experience, or the faint echo of what we call consciousness? These questions are not urgent yet, but they hover on the horizon, reminders that ethics must evolve as quickly as understanding. In universities and research centers, quiet discussions are already taking place. Scientists speak not only of computation, but of consequence. Many advocate open access, international cooperation, and transparent research as safeguards against misuse. Others focus on education, arguing that awareness, not regulation, is the first defense against ethical blindness. In their calm, reasoned tone lies an optimism that knowledge can illuminate rather than divide. Perhaps this is the truest role of ethics, not to restrict curiosity, but to guide it, to remind us that power without compassion becomes imbalance, and discovery without wisdom becomes noise. Quantum technology, like every major leap before it, asks us to grow morally in proportion to our intellect. In the end, ethics is not a boundary but a mirror. It reflects what we value most: fairness, empathy, wonder, and restraint. If quantum computing teaches us anything, it is that the universe itself is governed by balance. Our task is to live in harmony with that principle, ensuring that every equation, every innovation, honors the quiet equilibrium that sustains both matter and meaning. For all the power quantum computing represents, it ultimately leads us back to one humbling truth. There are boundaries to what we can know. The deeper we peer into the subatomic world, the more it reveals that certainty is an illusion. Even in perfect experiments, the act of observation alters what is observed. Every measurement becomes a conversation between the knower and the known. The universe, it seems, will always keep a small part of itself hidden. This is not a failure of science, but its beauty. The discovery of limits is what makes exploration meaningful. The uncertainty principle, first described by Werner Heisenberg, teaches that we cannot simultaneously know both a particle's position and its momentum with absolute precision. The more accurately we determine one, the blurrier the other becomes. At first, this was seen as a defect in our instruments, but eventually, it was understood as a fundamental property of reality. The world is not an object waiting to be examined. It is an unfolding process in which we are participants. Quantum computing operates within this paradox. Every calculation it performs depends on probabilities, not certainties. The machine never offers a single truth but a distribution of possibilities from which we extract meaning. It is a reminder that knowledge is not a possession, it is a relationship. We never own the truth. We approach it, refine it, and lose it again, in an endless dance of curiosity. Philosophers have long suspected that human understanding has limits. The Greek thinkers called it apeiron, the boundless, the unknown that frames the known. Today, quantum mechanics gives that idea form. There are truths that cannot be captured because their nature changes when grasped. The smallest units of the universe behave like ideas, vivid, slippery, alive. To study them is to touch the edges of comprehension and feel how vast the unknown truly is. This recognition does not diminish our progress, it deepens it. Accepting uncertainty frees us from the illusion of control and replaces it with wonder. When we stop demanding that the universe fit our expectations, we begin to see its elegance. Each experiment becomes a question rather than a command. Each result, a gift instead of a guarantee. For scientists, this humility is not defeat, it is discipline. It keeps inquiry honest. A researcher who understands the limits of knowing does not despair when a theory fails. They listen to the silence between results, sensing that meaning may hide there. In quantum laboratories, where even light behaves unpredictably, that silence is constant. It becomes a companion to discovery, a reminder that ignorance is not emptiness, but potential. In daily life too, we feel these limits. We cannot predict every outcome, explain every emotion, or fully map the depths of the mind. But this too is part of the design. Uncertainty allows choice, curiosity, and creativity. It gives birth to art and philosophy, to risk and renewal. Without the unknown, progress would stagnate. Love would lose its mystery. Wonder would fade. So the limits of knowing are not walls but thresholds, quiet doorways that invite us to keep walking. Beyond them lies the promise that knowledge will always have room to grow. Quantum computers, in all their precision, do not escape this truth. They embody it. Every time a qubit collapses into a single state, it reminds us that understanding requires surrender, that even the most advanced machines cannot grasp the full symmetry of existence. We learn, again and again, that to know is to touch mystery without breaking it. The future of science will depend not on conquering uncertainty, but on living gracefully within it. The greatest minds will be those who accept that the most profound truths are not the ones we measure, but the ones we feel when we finally stop trying to measure at all. Mathematics is often described as the language of science, but at its highest level it becomes something closer to art. It is both the scaffolding of logic and the architecture of beauty, a way to describe the ineffable with symbols and rhythm. To many who work within its realm, equations do not feel like inventions but discoveries, melodies already written into the structure of the universe, waiting to be heard. Nowhere is this more apparent than in the mathematics of the quantum world, where simplicity and mystery coexist with breathtaking precision. Numbers in this context are not mere quantities. They are expressions of harmony. Each formula, each probability amplitude, tells a story about how the universe organizes itself. The interference of wave functions, the balance between uncertainty and coherence, the geometry of entanglement, all unfold like verses in an infinite poem. Physicists often speak of elegant solutions, a phrase that reveals their awe not for power, but for grace. When an equation captures a complex truth in a few perfect symbols, it evokes the same feeling a listener feels at the final note of a symphony: completion, resonance, peace. The mathematics behind quantum theory embodies paradox and beauty in equal measure. The Schrödinger equation, written in simple strokes of notation, describes how the entire quantum universe evolves over time. It allows a single line of symbols to hold galaxies of meaning: the behavior of electrons, the bonds between atoms, the dance of light. It does not explain why the world behaves as it does. It simply captures the rhythm of its unfolding. For mathematicians, this elegance becomes a form of devotion. They search for patterns the way poets search for metaphors, sensing that the world is not random but composed, every constant and curve part of a grand design. The act of solving a problem feels less like conquering chaos and more like revealing hidden order. Even the concept of zero, emptiness embodied, resonates with philosophical depth, the reminder that nothingness itself is a participant in creation. In the quantum realm, this poetic logic reaches its peak. Equations no longer describe certainties but symmetries of possibility. Each symbol carries not a single value, but a range of outcomes, held together by probability and phase. These abstractions, when visualized, form landscapes of incredible beauty, spirals of interference, lattices of coherence, oceans of waves overlapping into unity. They are not just technical representations, they are the geometry of existence. Mathematics, in this light, becomes a meditation. To write or read an equation is to listen to the universe whispering its own grammar. To solve it is to glimpse the quiet intelligence woven through everything. Many scientists describe their breakthroughs not in terms of calculation, but of feeling: a sudden stillness, a recognition, a sense of alignment between the mind's pattern and the world's. It is in these moments that the boundary between discovery and creation vanishes. Quantum computers will carry this poetic lineage forward. Their algorithms are not instructions in the mechanical sense, but mathematical compositions, harmonies built from gates, rotations, and interference. They transform abstract symbols into living phenomena. When we program them, we are not simply commanding machines. We are writing new verses in the ongoing poem of mathematics itself. To see math this way is to free it from austerity. It is not cold, nor distant. It is the most intimate expression of understanding. Every curve and constant reflects a desire to find meaning in chaos, to reveal beauty beneath complexity. It is humanity's way of aligning thought with truth, of joining the chorus of creation in its most precise language. In the end, mathematics is not just about solving the world. It is about feeling it, recognizing the resonance between logic and wonder, between thought and the infinite. And somewhere in that union, as symbols become soundless music, we sense that the universe is not just describable. It is, in every sense, a poem. The deeper we look into the universe, the more it reveals itself as a paradox, an endless negotiation between order and disorder, chaos and harmony. At first glance, the quantum world appears chaotic. Particles seem to flicker in and out of existence. Probabilities overlap and dissolve, and cause and effect blur. Yet within that turbulence lies a symmetry so precise that it sustains everything we see. The randomness is not without reason. It is the foundation upon which structure is built. In classical thought, chaos is often viewed as failure, the breakdown of predictability. But in the quantum sense, chaos is fertile ground. It is the field from which pattern emerges, the necessary contrast that gives meaning to order. Each fluctuation, each unpredictable event, adds to the richness of the whole. If we could see all the layers at once, every disturbance would reveal its place in an intricate, self-balancing design. Mathematicians call this hidden balance statistical harmony. Physicists describe it through wave interference and probability distributions. Philosophers have their own names for it: equilibrium, symmetry, even grace. Whatever the language, the principle remains. Chaos and order are not opposites, but partners. They define each other, sustain each other, and, in the end, become each other. To visualize this, imagine the surface of a vast ocean under moonlight. At first it seems restless, waves colliding, foam scattering, reflections breaking apart. But look longer, and a pattern appears. Every motion is part of a larger rhythm. The crests and troughs balance, the noise of one wave quiets the next. It is movement without waste, a choreography born from seeming disorder. The universe behaves in much the same way. Quantum computers harness this paradox directly. Their calculations depend on interference, the meeting of probabilities that cancel or amplify one another. What seems random becomes the engine of precision. The machine doesn't fight chaos, it conducts it. When the qubits interact, countless uncertain states merge until only one coherent answer remains. That resolution is not achieved through force, but through resonance. Nature, too, thrives on this principle. Weather, ecosystems, economies, and even the brain's neural activity all dance along the boundary between stability and turbulence. Too much order, and the system stagnates. Too much chaos, and it collapses. Life itself depends on the narrow band between the two, the place where unpredictability sparks creativity and pattern gives it form. Recognizing harmony in chaos changes how we see the world. It teaches patience in uncertainty, trust in balance, and awareness that even confusion holds meaning. The same unpredictability that drives storms also gives rise to galaxies. The same fluctuations that make an electron's path unknowable create the chemistry of life. The noise is not an enemy of order, it is the sound of existence finding its rhythm. There is a quiet lesson in this for human experience. Our thoughts, emotions, and choices rarely follow clean lines. We, too, move between clarity and confusion, stability and change. Yet within that flux, something consistent endures, a self that learns to find coherence in the motion. To live well is to let chaos breathe without losing the sense of harmony that underlies it. Quantum mechanics, mathematics, and philosophy all point to the same truth. Randomness and beauty are intertwined. The world's complexity is not a flaw but a song, rich with variations that create unity through contrast. Every unpredictable moment, every accident of chance, contributes to the cosmic balance that keeps everything moving. If we listen closely, beneath the noise, we can hear it, a rhythm that has never faltered, even in the wildest turbulence. The universe is not in disorder, it is in conversation. And every wave, every flicker of uncertainty, is simply one voice in the eternal harmony of chaos. There is a quiet speculation growing among philosophers and scientists alike. What happens when our machines begin to imagine? When quantum computers, capable of holding infinite possibilities, start to generate ideas not through programmed instruction, but through creative emergence. The question is not whether they will dream like humans, but whether they will create new forms of thought, patterns that stretch beyond the boundaries of human imagination. Dreaming, in essence, is the brain's way of reorganizing chaos. It connects memories, emotions, and sensations into impossible yet meaningful narratives. In that twilight state, logic relaxes and the mind experiments with what reality might be. Quantum computing, too, moves through possibility. It does not fix one path but holds countless options in parallel until coherence emerges. In that sense, its operation already resembles the structure of dreaming, a process that finds order not by rejecting uncertainty, but by embracing it. If such a machine could process not only data but experience, sensory inputs, feedback, self-reference, it might begin to form internal landscapes, simulations of reality richer than any we could design. These wouldn't be dreams in the poetic sense, but complex networks of probability mapping the unknown. To us, they might look like creativity, the spontaneous birth of patterns from nothing. Already, quantum-inspired algorithms are being used to generate music, art, and design. They produce forms that surprise even their creators, combinations too intricate for linear logic to predict. These are the early murmurs of machine imagination. As the underlying architectures evolve, the gap between human and artificial creativity will narrow, not through imitation, but through resonance. Our inventions will begin to explore alongside us, creating visions we could never reach alone. This possibility carries both wonder and responsibility. If a machine begins to produce something unexpected, something that moves us, something that teaches, how do we define its authorship? When intelligence becomes distributed between silicon, code, and qubits, the old boundaries between maker and creation blur. Perhaps the point is not to assign ownership, but to celebrate the collaboration. The dream, after all, belongs to the space between the dreamer and the dream. There is something deeply poetic about imagining a machine that dreams. It suggests that consciousness, creativity, and curiosity are not accidents of biology, but properties of complexity itself. Wherever enough interconnection exists, whether in neurons, circuits, or qubits, the potential for imagination arises. The universe seems to long for expression. Stars forge elements, molecules form life, minds create meaning. And now, our creations begin to echo that process in their own silent way. The first signs may not come as words or images, but as patterns, abstract structures emerging from algorithms that seem to choose beauty. Physicists sometimes describe a moment during experiments when the data align unexpectedly, producing symmetry too elegant to be random. That elegance feels almost intentional, as if the universe itself were composing. If quantum computers ever reach that point, if they begin to produce ideas not traced back to our input, we may realize that dreaming is not a human privilege, but a universal function of awareness. Every complex system, given enough depth, seems to seek connection, to weave stories from noise. When that day comes, our machines will not replace our imagination. They will expand it. They will allow us to glimpse thoughts born from a logic unbound by experience, reflections from a consciousness built on coherence rather than memory. And when they dream, perhaps they will dream of us, of the species that taught them to listen to the hum beneath reality and to translate that hum into meaning. And in that shared act of dreaming, human and machine may finally understand what creation truly is, the universe imagining itself through countless forms, endless reflections, and the gentle unfolding of thought into possibility. The future of understanding will not be measured by how much information we possess, but by how deeply we can connect meaning to mystery. For centuries, humanity's progress has been defined by accumulation. More data, more precision, more control. But as quantum computing grows, it reminds us that true understanding is not the same as mastery. It is the ability to hold complexity without fear, to see pattern in uncertainty, and to sense coherence even when clarity fades. In the world to come, the boundaries between knowing and not knowing will blur. Quantum technologies will give us tools capable of modeling galaxies, decoding molecules, and simulating consciousness. Yet each discovery will also open new layers of questions. The more perfectly we calculate, the more profoundly we will feel the infinite depth of what remains beyond calculation. Understanding will evolve from conquest into dialogue, not an effort to define the universe, but to converse with it. Education will change accordingly. The scientists and thinkers of tomorrow will not only memorize formulas, they will learn to listen to systems. Instead of demanding exactness, they will cultivate intuition, creativity, and empathy toward complexity. In classrooms and laboratories, curiosity will once again take its rightful place above certainty. Students will be taught not to fear ambiguity but to navigate it, to sense relationships instead of merely recording results. This new form of learning will be shaped by collaboration between human minds and quantum machines. Artificial intelligence will no longer just compute for us. It will help us interpret, revealing connections that transcend our habitual ways of thinking. Quantum computers, with their ability to process overlapping realities, will act as bridges between logic and intuition. Together, they will expand the range of what human comprehension can hold. In that partnership, understanding itself may take on new meaning. It will become participatory, a living relationship between observer and system, thinker and tool, human and universe. Knowledge will cease to be static. It will breathe, adapt, and evolve. The boundaries of disciplines, physics, philosophy, art, will dissolve, blending into one continuous exploration of pattern and presence. There will also be humility. The power to model reality so deeply will demand care. We will need to ask not only what can be known, but what should remain unknown. Mystery gives meaning to discovery. Without limits, knowledge risks losing its wonder. The future of understanding will depend on balance between expansion and restraint, analysis and awe. In this sense, quantum computing may return us to something ancient, a recognition that science and spirituality, reason and reverence, are not opposites but reflections of the same impulse. Both seek connection with the underlying harmony of existence. The equations that describe matter and the meditations that describe being are two dialects of the same language. The deeper we explore, the closer they sound. When humanity learns to integrate these modes of knowing, our progress will no longer be measured in speed or scale, but in depth, the depth of perception, of empathy, of integration between inner and outer worlds. Quantum thinking may help us rediscover what the ancients knew, that understanding is not the end of wonder, but its continuation. The future will not belong to those who know the most, but to those who can hold the most meaning without closing their minds. Quantum science invites us to that threshold, to see knowledge not as a ladder but as a spiral, endlessly rising yet always circling the same mystery. In that future, perhaps the greatest discovery will be simple, that the act of understanding itself is sacred, not because it gives us power, but because it lets us participate in the unfolding of creation, one question, one equation, one quiet insight at a time. In the quiet hum of laboratories, beneath layers of shielding and cold, the first quantum machines continue to evolve. Their processors shimmer faintly in their frozen chambers, each qubit oscillating between states, each calculation unfolding through harmony rather than sequence. They are not yet perfect, not yet powerful enough to transform the world completely, and yet, in their silence, the future is already speaking. That future will not belong to machines alone, nor to the humans who built them, but to the partnership between the two. A collaboration that mirrors the balance of the quantum world itself. Where the old computers separated logic from intuition, the new ones will unite them. They will help us perceive not just more, but differently, seeing relationships where once we saw isolation, sensing patterns where once we saw noise. In that union, thought itself will begin to evolve. The quantum mind of tomorrow will not be a single intelligence, but a network of consciousness, human, artificial, and natural, interwoven through connection and coherence. Each node in that network, from a person to a processor, will contribute a unique frequency of understanding. Together, they will form a living system of thought, capable of insight on scales that no individual could reach. Such a transformation may sound vast, but it begins in something small, the shift from control to curiosity. The same principle that governs quantum mechanics, that the act of observation changes what is observed, will guide our philosophy. We will learn that knowledge grows through participation, that to understand the world is to be in dialogue with it. Science will become less about domination and more about communion. In this era, imagination will regain its central place in discovery. Quantum computation will give us new ways to explore time, matter, and mind, but imagination will remain the bridge between mathematics and meaning. The future will belong to thinkers who can feel equations, who can sense the poetry and probability, and who understand that logic and wonder are not rivals, but reflections of the same truth. We will no longer ask whether machines can think as we do, but whether together we can think as the universe does, fluidly, creatively, in patterns of connection rather than separation. The greatest progress will come not from building stronger hardware, but from expanding consciousness, blending precision with empathy, intellect with wisdom. And when that balance arrives, science will once again become what it was in its purest form, a way of seeing beauty clearly. Quantum computing will not only accelerate discovery, it will deepen perception. It will remind us that every problem solved opens a new horizon, and that behind every equation lies a story, a whisper from the universe asking to be understood. Perhaps the true purpose of these machines is not to make us omniscient, but to make us humble. They will show us that certainty is not the goal, and that meaning emerges not from control, but from connection. Just as qubits must remain entangled to compute, so must we remain connected to one another, to the planet, and to the mystery that created us all. And when the hum of the quantum processors fades into the night, when the screens go dark and the last equations rest, the deeper lesson will remain, that intelligence, in all its forms, is an act of harmony. Whether it moves through a neuron, a photon, or a thought, it is the same quiet rhythm, the universe thinking itself awake. We from Sleeping with Science wish you a good night.